Welcome back. The agenda for today is the revision of functions, and we will study composition of functions. In earlier chapter, we defined function as a set of ordered pair in which each first component is paired with only one second element, and we solved some problems in the problem section of that chapter. The implication of the function as we defined earlier were each element of domain must get assigned and no element of domain can be left unassigned. The second one was domain will be assigned to exactly one element of the range. The third point was a element in range can be assigned by more than one element of the domain. Another point was some element of domain may not be assigned by any element of A. This we have already seen in the last chapter, and we solved some problems also based on that chapter. We also defined what is domain, what is range, what is a dependent variable, what is an independent variable. For this, earlier chapters may be referred to. We know that graph of a algebraic expression exists and can be plotted. However, it is important to understand that not every graph represents a function, right? Now we are moving from function definition from ordered pair to a graph of algebraic expression. What I just said is a graph of algebraic expression can exist and can be plotted. What is an algebraic expression? You know very well. Suppose this is an algebraic expression. The graph of this algebraic expression can be plotted, but whether this algebraic expression's graph is a function or not, we have to understand. It is very important to understand. When we apply the above definition of ordered pair, that each first component is paired with only one in the range, then that is applying above definition of function, we can not have two values of y assigned to one value of x. Thus, this is summarized in the famous vertical line test. What I have said, suppose this is x, this is y. An element cannot be assigned to two values in y. That the same which was happening in the ordered pair definition. The meaning of this in terms of graph is that a vertical line test. What is this vertical line test? Suppose this is a graph of a function. This is xy axis, and graph of function is just like that. This is x-axis and this is y-axis. Now we plot vertical lines parallel to y-axis like this I have drawn. If these vertical lines cut the graph at 2 points, then what will happen? Suppose this is the graph. This vertical line cuts the graph at these points. As can be seen. So 3 points are being cut by this vertical line. So at this x value, suppose this x value is x1, we are getting 3 values of y. 1, 2, 3. I will draw a bigger graph. So this is a graph of a function. We draw a vertical line. This is suppose x1. For this x1 there are 3 values of y. y1, 4 values. y2, y3, y4. But our definition of function says a value of x can have single value of y. So what is the vertical line test? If the vertical line cuts the graph at more than one point, then that graph is not a function, not a graph of function. As it failed, vertical line test. So what is the formal definition? A formal definition of vertical line test is a graph in xy plane represents y as a function of x provided that vertical line intersects the graph at most one point. It may be possible that there is no intersection. Suppose this is the graph of a function, this one is the graph. It is cutting once only. It may be possible that it does not cut the graph. So at most once. Any word, suppose this is, we draw a vertical line here. This is a vertical line. This vertical line here. This is, I will draw again. Suppose this is the graph. This is axis. Our graph is like this. We draw a vertical line like this. This is a vertical line. This vertical line does not intersect the graph at any point. So this is a graph. We have to draw many. We have to test at all the points on the graph. What the definition is, we draw many vertical lines. However, each vertical line will cut the graph at most one point. If it is cutting at 2 points, then the algebraic expression graph is not a function. Now how to define its implications. For intercepts. We have defined intercepts in one of the lectures. Suppose this is the graph. This is the x-intercept and this one is the y-intercept. this one is the x-intercept. It may happen that if the graph cuts at many points, a vertical line tests many points, then y-intercept may be this one also and this one also. So if the graph is not a function, then we may have more than one y-intercept. But if the graph is a function, then we can have at most one y-intercept, but more than one x-intercepts are possible. So I have defined a function in terms of a ordered pair. Then the same definition of ordered pair we take to the graph of algebraic expression, and we defined that for a graph of algebraic expression to be a function, the graph should pass the vertical line test. That is, vertical lines drawn on the graph can intersect the graph at most one point. It may be 0 also or 1 also, but more than 1 is not permitted for definition of a function. Now, how to find the domain and range of a algebraic expression or any graph from its visualization. That is, the graph is given. How do we define its domain and range? The portion of x-axis at which the graph is drawn, it is called the domain. Suppose this point is minus x1 and this point is x2. So the domain of this function is minus x1 comma x2. There is a nomenclature. Suppose this is nomenclature a dark point and a open point. If it is dark point, then this point exists on the graph, and if it is open point, then this is the end point on the graph, and the end point is not on the graph. That is, suppose that is graph extends just before x2. x2 is not on the graph. As we have discussed earlier, the domain will be x minus x1 is on the graph, x2 is not on the graph. So we draw this kind of bracket. Similarly, what is the range from this graph? This is the range. That is, we want to identify the range and domain from a graph. It can be easily done just by visualization. Now we are moving towards a combination of functions. Combination of functions. We know that if there are two real numbers, a comma b, we can combine them in the form a plus b, a minus b, a into b, a divided by b. A comma b belongs to real numbers. Similarly, two functions can be combined to create a new function in the similar manner. Suppose two functions are fx comma gx. Then in the same way as we combine the real numbers, the functions can be combined. The functions can be combined in this manner. F plus g x is equal to fx plus gx. F minus g x is equal to This is what we are doing, arithmetic operation on functions. Arithmetic operation on functions. So these are addition, subtraction, multiplication, then division. Our gx cannot be 0 because it is coming in the denominator. What is the domain of these the functions obtained after the mathematical operation? The domain of these functions is the domain of the intersection of domain of f intersection domain of g. Similarly, this is our same. Similarly, this is the intersection of the domain of a function f with the intersection, that is the common points. What are the common points in the domain of f and g? Are the domain of the addition of these two functions. I will give example. Similarly, for multiplication also, however, for this the domain is domain of f intersection domain of g, but exclude point at gx is equal to 0. Suppose this is our function f1 f. This is our function g. The intersection of these domains are this one. So the domain of the f x plus gx is this one only, where these two, the domain of both functions intersect, or where the domain of both functions is common. I will draw a graph in different color. This much I remove. Suppose a graph is this, like this, this one, and another graph is graph of a function is this one. So what is the domain of this whole graph is this much, and domain of this graph is from this point to this point. So what is the common? This point, these two, where both functions exist simultaneously, is the domain of this fx plus gx. Fx plus gx does not exist at these points, right? So domain of fx plus gx is this one only. This you have to keep in mind. So now we have defined arithmetic operation. Another operation on functions is composition of functions. I am teaching all this just so that the concept of inverse of a function may be made clear to you. What is composition of a function? I will define very easily. Suppose we have two functions, fx and gx. That is, both of the functions are passing a vertical line test. So these are functions. What we do, This is gx function. We give an input x, we get an output gx. This is g machine. Now suppose we give an input of gx to another function fx, f machine. Instead of giving input x, we are giving input gx to this machine. Then what will be the output of this machine? Output of this machine will be f of g x. We represent it like this: f of g x. This is how it is. It is equal to f of g x. In the whole system is now defined like this. We give input x, there is a machine f of g, we get output f of g x. I give an example for this, then things will be clear. Right, suppose fx is equal to x square and gx is equal to 3x plus 1. Right, so what is f of gx is equal to gx is this one. So we put this value in x, this value, then f of gx will become 3x plus 1 whole square. That is in place. Here is x, so it will become x square. If it is g, it will become gx square is equal to gx square. This is our f of g. Similarly, we can also find g of f is equal to g of f x is equal to g of f is equal to g of f x is equal to g of fx. That is, start with x as input to fx, then gx as fx as input to g to calculate g of fx. It will improve our understanding of the inverse, which we'll define later. Now, what is the domain of this? The domain of a composite function. We define composite function in two ways: g of f or f of g. It can be any number. You can define any function inside. The meaning of this is, meaning of f of g is, first apply g, then apply f. This is formal definition of a composition of function. It is denoted, the composition function is denoted by f of g, and it is f of g x is equal to f of gx. Domain of f of g x is the set of all x such that x is in the domain of G and Gx is in the domain of F. I will explain it further. As we have seen, the composite function is defined like two machines. First, we get a G machine. We input the x, we get Gx. Then we input the Gx into a F machine. F machine, we get f of gx. So the domain of this machine is x. And what is the domain of this machine? The domain of this machine is this one. That is f exists at what points at which gx is defined. So the domain of these two functions is such that x is in the domain of g and gx is in the domain of f. I will give an example for this to make you understand what is the meaning of this. And I write again, x must be in domain of G and Gx must be in domain of F. That is, for finding the domain, we exclude points, exclude the following. If x is not in domain of G, it must not be in domain of f of G. Another point, any x for which Gx is not in domain of f, then it will not be in domain of f of G. I explain it further. This is the method to find the domain of f of G. I give example. ये क्या हो गया?